In this lesson, we're going to study arc length of space curves. So suppose we have a space curve with vector equation r of t equals f of t, g of t, h of t. And let's suppose that our derivative functions, f prime, g prime, h prime, are continuous functions, and that our curve is traced exactly one time as t increases from t equals a to t equals b. So given those conditions, then the length of our curve, meaning if you stand on our curve at the point corresponding to t equals a and walk along the curve to the point corresponding to t equals b, the arc length of that curve is given by integral a to b square root f prime of t squared plus g prime of t squared plus h prime of t squared. Or if f of t, if you think of that as your x component, dx dt squared, dy dt squared, etc. So this is our familiar arc length for parametrically defined curves from two dimensions. Then we just have this third plus dz dt squared component, given that we're looking at a vector curve in 3 dimensions. So here's our formula, and now let's take a look at an example. So here is our helix curve. So this is the circular helix that we've seen before. So here is our the graph of this space curve. So our vector equation, we've seen this curve before. The vector equation is r of t equals cosine t sine t t. And we said this was a circular helix because it satisfies x squared plus y squared equals 1. So you're a circle in the xy plane climbing up the z-axis. So I want the length of the arc of this helix from 1, 0, 0 to the point 1, 0, 2 pi. So first of all, let's just make sure these really are points on our space curve. For the first point, 1, 0, 0, I notice my third component of r of t is just the function z of t equals t. So in order for this point 1, 0, 0 to be on the curve, it would need to correspond to t equals 0 because my third component here is 0, which needs to be equal to t. So let's see what r of 0 is. Well, r of 0 is cosine 0, which is 1, sine 0, which is 0, and t equals 0. So 1, 0, 0 is the point on the curve corresponding to t equals 0. And what about this point here? Again, in order to be on this curve, my third component is 2 pi. That would need to be t, so t needs to be 2 pi. So now let's check. What is r of 2 pi? Well, it's cosine 2 pi, which is 1, sine 0, which is 0, and t is 2 pi. So this second point is also on my curve. So what the question is asking me is saying, if I stand on the curve at the point corresponding to t is 0, and I walk along the curve until I hit the point corresponding to t is 2 pi, so if I trace around this curve until I hit the point t is 2 pi, how far have I walked? So we can answer that question using our formula from the previous page. So t goes from a to b, so in this case 0 to 2 pi, the square root of derivative of the first component, derivative of cosine is minus sine squared, derivative of the second component, so cosine of t squared, and derivative of the third component, so 1 squared dt. So this gives me the square root, the integral from 0 to 2 pi of the square root. Sine squared plus cosine squared is 1, so I just get 1 plus 1 dt. So I get integral 0 to 2 pi root 2 dt. Evaluating that integral, I get root 2t evaluated from 0 to 2 pi, or 2 pi times the square root of 2 minus 0, so just 2 pi root 2. So if I stand at the point 1, 0, 0 and walk along the curve to the point 1, 0, 2 pi, I've covered a distance of 2 pi times the square root of 2 units. So the key parts to this problem were using our formula for the arc length and identifying the a and the b, so the t values. In this case, it was t going from 0 to 2 pi. Those are the t values that corresponded to the points on our space curve.